Alright, so in this video we're going to prove the triangle inequality. And it's funny that in mathematics may be the only instance where an inequality is actually nice and useful. Well, either way, the triangle inequality states that the length of the sum of two vectors a and b never exceeds the sum of the lengths of the individual vectors a and b. And we can visualize this inequality by making a triangle out of a, b, and the sum of a and b, because the way that we add vectors is we first draw our first vector, a. If we want to add the vector b to it, we think about placing the tail of the vector on the head of that vector, seeing where that ends, and then going from the tail of the original vector to the head of the second vector, and that gives us the sum of a and b. And so what the triangle inequality tells us is that the length of this side never exceeds the sum of the lengths of the other sides. And this is a self-evident fact about triangles, but something that does require a proof. So we'll provide that proof in this video. Okay, so we won't go to directly prove it. We're going to prove an auxiliary result first, called the Cauchy-Schwarz inequality. And so even though this inequality has two mathematicians' names attached to it, it's actually incredibly simple, and you'll see just how simple it is. So what the Cauchy-Schwarz inequality says is if we take the absolute value of the dot product of two vectors, remember when we do a dot b we get a scalar, so it's a positive or a negative number, it's a real number. Then we take the absolute value of that real number, and the claim is that this never exceeds the product of the lengths of the individual vectors a and b. And so to prove this Cauchy-Schwarz inequality, all we have to do is think about our geometric interpretation of the dot product. So we know that the dot product of a and b is just equal to the product of the lengths of a and b times cosine of the angle between the two vectors. So we think about a and b as two vectors emanating from the same point, the origin, for example, theta being the angle between them, and then we know that the dot product of a dot b is equal to the product of the length of a times the length of b times cosine of the angle between them. And so there's a video up where we prove this geometric interpretation of the dot product, so you can consult that video if you want to see how that's derived. Okay, so either way, this is where we start to prove the Cauchy-Schwarz inequality. And so I already have my dot product. I need the absolute value of the dot product, so I'm going to go ahead and take absolute values of both sides. And so, of course, length of A, length of B, those are both positive quantities anyhow, so I won't do anything with them. Cosine of theta can be positive or negative, so I'll put an absolute value there. But then we know that the absolute value of cosine never exceeds 1, and this is literally all we have to do. Replace cosine, absolute value of cosine with 1, and we get something that's larger, and we're left with the product of the lengths of the individual vectors. And so that proves the Cauchy-Schwarz inequality. Like I said, incredibly simple, even though it has two mathematicians' names attached to it. And so this triangle inequality is actually a fairly simple consequence of the Cauchy-Schwarz inequality. So let's see how that all fits together. Okay, so we want to consider the length of the sum of two vectors a and b, and so I won't consider it exactly as this. I'll look at the square, and the reason I'll look at the square is because I know a relation back to the dot product when I look at the square of the length. And this is also in the video about the geometric interpretation of the dot product, so you can watch that video. And so we know that this is equal to, if we take the vector itself, which in this case is a plus b, and then just dot it with itself, right? Any vector dotted with itself gives us the length of that vector squared. So in this case, a plus b is our vector, and so we go ahead and dot it with itself to get the length squared. And then we know about the vector distributive properties of the dot product, so I'll go ahead and just use them. So this turns into a dot a from this. We have an a dot b. We have a b dot a, which we know we also have a commutative property, so those are actually the same quantity. And then we also have a b dot b. But like we were just saying, we know that a dot a is just the length of a squared. Like I said, we have the commutative property, so a dot b is equal to b dot a. So this is really just 2 times a dot b. And then b dot b is just the length of b squared. Okay, we're basically there. And so now at this point, I see that I have a dot b, and I know that a dot b, even in absolute value, is less than the product of the lengths of a and b. So this could be positive or negative, but either way, I know that it's certainly less than its absolute value. And when I replace it with this quantity on the right from the Cauchy-Schwarz inequality, right, this is just going to be 2 times the length of a times the length of b. I know this is greater than the quantity that I originally had, and then I have the length of b squared. Okay, and that's almost it. And now I just have to unpack this quantity. I notice that this is a perfect square. It is the length of a plus the length of b, quantity squared. And so now I notice that I have some positive quantity being squared is less than another positive quantity being squared. The reason I mention that those quantities are positive is because when I take the square root of the square, I'll just retrieve the original quantity. And so what this is going to prove is that a plus b in length is less than the sum of the length of a plus the length of b. And that proves the triangle inequality for us. So there's a nice geometric picture to refer to in terms of side lengths of triangles, and then there's also this rigorous proof based on the geometric interpretation of the dot product, which leads us to the Cauchy-Schwarz inequality, and then immediately as a consequence we get this triangle inequality. Alright, I hope you learned something in this video, and I'll see you next time.